Okay, welcome back. So we had these big breaks because of all of the. Oh, is this what's happening here? Good. Alright, let's see if I can adjust the camera there. Should be okay. I think this might be the best we can do. Alright, welcome back. So we had these big breaks because of the travel, but it's always very enjoyable. Let me just gonna post on Twitter as well that we are live. It's always very enjoyable to travel. It's always nice to meet people, but I'll say it again. Every time I go somewhere, I'll run into someone who'll tell me something like, "Oh, I've been using SemiBin," or I've tried to use the GMGC, or I tried to do this with, and then they'll ask me a question, and I'll try to help them. But I just want to say that if you're one of these people that is running one of our tools, please feel free to just get in touch. We don't have to all go all the way to South Africa for a conference or meet in San Francisco or wherever else. So if you're using one of our tools, one of our resources, if you're wondering whether you can use the GMGC for whatever, or whether or you're struggling with some aspect of SemiBin, please just get in touch. Email us. Our preferred medium of communication is to use one of the public mailing lists, but otherwise, we can even schedule a Zoom or something, because yes, it repeatedly happens that, and I don't want to single anyone out. It's always lovely to meet people in person, but we don't need to wait all of that. We don't need to wait that time. We're live now. Let's see, there's something. Let's see, there's some. Let's see, maybe I need to. So I've also updated my computer, so there's. Something. Oh, I see that. Okay, I see this. Okay, I updated my computer yesterday and just checking that everything works. Okay, all right. Let's go back to. Let's go back to where we were in terms of science. All right, so. Let's go back. Where had we left off? So, see where we are. Okay. So we had left off where, and where we. I'm gonna just show. So we had seen that indeed. When we introduced mutations, and we were doing everything with simulation, when we introduced these simulated mutations, we are able to. I'm going to do edit settings. When we introduce this. When we introduce the simulated mutations, we're able to see that we have. Is this okay? Let's see. I'm sorry. I'm trying. I think this is. YouTube says we're good. So we introduced these simulated mutations. We saw that there's shorter genes, and then we've been struggling for the last several sessions on figuring out what does shorter mean. So what should be the right reference to use to define shorter. And so the idea we had a couple of weeks ago was, okay, we will use the GMGC because then it's, first of all, should include prokaryotic genes from the microbiome, so that should be the right population, and then we can filter so that we only have the complete genes, right? And so So we're going to do the exact same annotation of the GMGC that checkm2 uses, and then since checkm2, and then maybe we can use that as a reference and reuse the checkm2 outputs, right? So last time we wrote code. Here, this is in this chug file that was going to run run this diamond process, which is exactly the same as checkm2 uses, but we would run it on the GMGC, only the complete ones. And then I said, okay, I didn't run this on stream because this would take a long time, so I'm just gonna leave it running. And unfortunately, this didn't. This eventually did something, and it seemed to either crash or and partly even on a. So I've said that for this project, I want to do things that you can run on a standard laptop. So and this seemed to be a little bit. It's a little bit too much if always say you can run this on your laptop, but there's this one step that takes several days of just leaving. It's a little bit fragile. So today I'm gonna do something that's actually very fits very well the jug model, which is we are going to split up the inputs into a bunch of little, little quote unquote little. So just let's say we split it into 1 million genes each, or maybe that's still too much because there's about 100 million genes of input. So maybe we split it in, let's say, 2 million genes each, so that now we have 50 inputs. Then we run it individually on each of the 50 inputs, and then we concatenate the results. Right? So let's do it that way. Okay, so this, all right. So here we need what we need to adapt. Okay, let's do. Okay, so maybe instead of jug file, first of all, let's start there. Instead of jug file, okay, let's make this a little bit. Okay, this here run diamond. So instead of running the whole thing, we're going to have to give it, input file. And then here the output file. Yeah, this. Okay. Yeah, no, nothing like this. File number sequences per chunk. Okay, do we have? Okay, we have a faster file. We have a faster file processor there, or so let's do. So we do something like this. For HCKIN faster. Is it? Okay, so we're gonna read the input. Correct, 0. Okay. How does this work? Something like something like this. Not bad. Something like this. Yeah, is it? Next, right. Okay, something like this, right? So, output files empty. So we start to, let's just gonna collect all the output files in here, and then this. So we need to do this. We need to do this in a slightly awkward way, but otherwise we end up repeating code, right? But so we initialize this way. So this is the number to trigger. So this will trigger a new file at the start. So we initialize it to be. So we initialize this here, so that in the very first iteration it will trigger a new file. Index equals 0, and there's no O file is none, and then right. So this is the number of sequences we have. So if we're number of sequence per chunk, then okay, if there's a file we close. Otherwise we reset the counter. The number. Okay, we generate a new file name, we open it, we set the compression level equals 1 because we will eventually be just deleting these, so these are just temporary. So there's really no point in compressing this very much, and that's it. And chunks equals, yeah, something like this. Something like this. Actually, let me just see that our file would be. Like this. But something like this. I think this is probably. And now, okay, I'm going to start running this. Okay, forgot the import. Okay, this is sounds about right, right? So this is not. There's one thing that's not really great is that the files are sorted so that the shorter sequences appear first, which unfortunately means that we are going to have the first chunks are going to be slightly shorter because those will be shorter in terms of number of base pairs, even though they have the same number of sequences. So we can see sound is a little low. Okay, I'll put it a bit up. I'll just move the microphone also a bit closer. Should be it. Yeah, I tested the sound earlier and it seemed okay, and then actually it seemed a bit too loud, so maybe I over adjusted it in the end. Okay. Right, so hopefully it's a bit better with the sound now. Okay, right, so yeah, so you can see that they are getting a slightly, yeah, this is okay. This will probably be, right, so we have these chunks, and now and alright, so now this run diamond will take the input and so I'm leaving everything else the same, but I am going to unlink the I file. So unlink is the, alright, thanks for confirming that the sound is better. So unlink means that, okay, it's just remove. So alright, so I'm now gonna, right, so let me see if I find, show you. So this is a very standard, even in the original manuscript. Oops, sorry, didn't mean to do that. Even the original manuscript for Jug. So we had this, right, this type of structure. Yeah, this type of sort of fan in, fan out structure, right? So we load the inputs. We're going to split up the input into. So this is the big GMGC file. Then we generate all of these chunks. We're going to process each chunk individually, and then we're going to collect it. So sort of this fan in, fan out. Jug is basically designed for this exactly this type of thing. Yeah. So I don't know, KO chunks. All right. So there's that. Okay, now it's running. Okay, so it's going to split the file. So let's see how. So yeah, so we said that it's a little bit over 100 million genes. Each chunk has each chunk has 2 million, and so we should expect that the output. You should expect about 25 output files, right? And so that's probably what we're gonna get. We should expect about, I did that math twice, I should expect about 50 output files. Let's see. Notes. Okay, we can see we've, okay. Chunks of, so here, more manageable, more robust. So it really has been the robustness that was the problem, where I tried to run it and it would just not finish. It would take several hours. This way, it takes several days even. So this way we'll have, I think my expectation is that 2 million, it's going to be a while, a couple of hours, but but it will be a manageable amount of computation. All right, so this, I'm going to commit this, split GMGC. So this is very, yeah. Okay. Okay, again, all right, so now, yeah, now we need to, yeah, and then at the very end we would need to have to write code that concatenates everything, but maybe that we can wait for next week. So all right, so let's see where we are in terms of time. Okay, so gone for about 20 minutes. So let's. Oh yeah, so here I can show you. So this at least this was when I was running Diamond before, and so it ran for 8,000 minutes. So that just give you an idea. Yeah, so that's 137 hours. Yeah, so it ran for almost a week. And then I was also traveling. I was using. It was just very unmanageable. Okay, let's see. Cleaning up a little bit here. So this was the explorations we were doing last time. Okay. Okay, so we still have about 30 minutes. So let's see. So one thing that I think eventually we will want to do, so alright, so I'm just loading this code we had before. Okay, and this, so this was using the uniref standard for the for the size of the genes. Oh. Okay, so in the past we've looked mostly at we've looked at this, and we were looking at the percentiles or the positions of the, so we were looking, so for that KO, this ORF is large or small, and so we did a bit of filtering to only include, so we wanted to only include KOs that had, at least, so for example, yes, for example, this one, there's only one, so there's, is it larger or smaller? Well, this one has 10, so 10 is not that many, but this one has 900, so this one's probably a good, let's see, a good reference. And Okay. Sort them. Okay. Okay, and again, okay, this is the problem with this. Problem with this reference is that many of these are probably partial genes, but we can still see that there's this here 507 to, oops, so did I mess this up? Okay, I messed this up somehow. Yeah, so 507 to 450 or to 550. So this is a pretty tight. So this is a pretty tight. So it's pretty obvious that these are partials, right? Here, probably. And probably, yeah, probably. So this jumps here. So before we were just using the position, the percentiles, but this is not very. But we probably do want to use something more along the lines of mean and standard deviation. Yeah. So something like a z-score or z-score. Probably. So let's do the same thing we were doing before, but whereas before we were so here before we were just looking at the percentiles. Let's see if we can do this looking at the z-scores of sizes. Okay, let's do because there's more information there than just a percentile, right? And there's and in the subsequent step we can even think that instead of using all the KOs, we will find KOs that are better than others. So I'm just checking on the other computation, the splits. Right, so okay, so we're splitting up to 44. So we'll be soon done with this. Yeah, so this will be 45. Yeah, okay, so this will soon be done. Okay, I don't think okay, I'm gonna do something. I'm actually gonna kill it. Okay, I'm gonna do something a little bit. Okay, I'm just yeah. So I just changed so that it's a 2-digit number. Yeah, this is completely an aesthetic preference, but just it would just annoy me the whole time. That that the order looks like this: 0, 10, 11, 1, 20, 2. So this way the order will look nice. Yeah. And okay, so it's going to take this time. So let's check back in about 10 minutes. Okay, so where were we? Okay, so we said we had done this with percentiles. So instead of percentiles here, let's do. Oops, sorry, let's stop here. Okay, we had done this. Okay, so this is what we want is so these scores append. Yeah, this is actually pretty good. Yeah, it's actually pretty good. Yeah. Okay, something like this. Okay. Okay, we have. Okay. Oh yeah, okay, this is not percentiles anymore, so this makes absolutely no sense. Yeah, maybe this plot makes no sense. Let me just look at what we're doing here again. Okay, the previous plot makes sense. The score, if I could spell the score, yes, this plot makes sense. Right, so this makes sense. So this is the z-score of the different so all the ORFs by KO, and you can see that basically there's a clear enrichment. So now it becomes even this is actually much nicer than before. And now this, I don't know what this is. So this plot made a lot of sense. I think this plot made a lot of sense for when we had percentiles, but when we have z-scores, yeah, this doesn't make sense because yeah, something like this would make sense. Let's yeah, like this makes sense. Alright, so this is now the sort of the cumulative distribution. It's cumulative distribution, and so let's say from -4 to +4. Right, so the blue and orange lines are the sort of wild type and 100. So we can see the orange already, and then with 1,000 mutations, right, we have a lot more. Alright, this is pretty good. So KO length z-score. So now this is actually z-score. Yeah, this makes sense. Alright, let's do this. Let's run this for all of them. and now it's gonna take this is gonna take a little bit. Let's check the other process. Okay, the other process is running. So okay, so now the ordering is also slightly nicer. You see, like 0, 0, 0, 1. We're up to 19. Let's check. So it's been running for about 6 minutes. So that should be done. Should be done in a couple more minutes. Okay, and we can see it now. Okay, here are the different plots for the okay, yeah, this is nice. So I think the big difference that I'm now seeing here is that unlike the previous approach, where even for the where we'd have huge, so in the previous okay, yeah, this is nice. So in the previous approach, or the previous visualization with percentiles, we saw this issue where, for example, this was the Campylobacter, so where Campylobacter just had shorter genes overall. So, and actually at ISME I talked to some people about this, and apparently this is, you know, I said, oh, I hadn't seen this as usual, or not, maybe not as usual, but in this, at least in this instance, was my own ignorance. Apparently it's known that, for example, you know, these ocean microbes that are very, very streamlined, they're even streamlined at this level where their genes are known to be short, because they're really optimizing for every nucleotide. And so Campylobacter, obviously not an ocean microbe, but it is known that some microbes are just shorter. But when we look at the, so maybe there is a difference there, right? If I look at this, maybe there is a difference. Let's see. But still, if I look here at -2, especially they're really, so this is Campylobacter, there is a big, so it feel, maybe not. Maybe once we clean up, but it still feels less. Still feels that, yes, if we look there, -3, it really does go very close to 0. So it can, and this was more, here was even more apparent. Yes. See, with 1,000 mutations, you start to see a lot of genes that are like in this -6. To actually be, maybe we could also, like this would also be the case where selecting particular KOs that are more stable in terms of their size would filter out some of these, and then only these would remain. Alright, but that's a signal there. Okay, this is Z-score. Oh. Actually, let's check this. So is it? Check there. Okay, that keeps going. Let's just check this. So we have. Does select work? Okay, now I'm trying to remember polar syntax. Select. Yeah, okay, yeah, filter. Filter. Right, so how do we do this? Polars. Select columns by type. Select columns by type. Oh, yeah, so filter with select. Okay, we could do this. Let's see how it does. Okay. Different. Okay, this works. So not great, but it works. All right, so. Okay, this is nice. Okay, this is closer to what I want. I mean, at least it seems to give. Skip all this plotting. Okay, and while that runs, let's just check in. Okay. Okay. Okay, yeah, okay, we had forgotten this one variable there. But now, alright, so now it runs, there's 48 diamond tasks, but they will probably all be, so I will run. So if we had access to a cluster, or then we could even run these 48 at the same time if we had the cluster with 48 compute nodes. But we can also just run them one by one, which is what we'll do. But this will be hopefully much more robust than the equivalent way of doing things before, which was just do it at once. So you can see there are diamonds running. Yeah, so when I do this on the stream, everything runs super slow because OBS is also running for the streaming. But then this should be okay. But this should, okay, so this should eventually just finish. So each task should take a reasonable amount of time, unlike previously where it would, you know, as I said, it ran for 5.5 days and then something bad happened. This way, each one will probably take a couple of hours. You know, still a long time, but 48 times a couple of hours, that's, you know, that's a hassle, but a manageable one, as opposed to something that's just disrupts your workflow for a while. All right, so we're sort of going back and forth between these two tasks. So actually, I am going to just amend. So I'm just going to amend the previous commit because the previous commit was a little bit buggy. So let's just amend that. No reason to have our history, the Git history, have all of this, you know, screw ups. So we're going back and forth. This is not uncommon that we have some task that takes a bit more compute, and so it runs a little bit slower. And then once we do that, we go back and forth. All right, but we can see here. So this is actually, surprisingly, it's echo line that has it still has a couple of genes that are really much shorter than expected. Maybe this will go away. But still. But we would want to have, we could even do the math on this, right? If the z-scores were perfectly distributed according to a normal distribution, and we have, you know, let's see, we have 1,000 of them for Staph aureus, so 1,000 of them, if they're perfectly normal distribution, we expect. Actually, this is tighter. This is, yeah, we'd actually expect more to be -2, right? Because -2, that's yeah. What's it? Yeah. What's the math? That's 4. We'd expect 4% would be below -2, right? Right about that. And so we'd expect about 40 to 50 and not 13. Right, but this is 50, but certainly not 84. Yeah, so maybe this is the signal we're looking for, is this. I was thinking that we would go up. So this is, so what we're looking at, so this is the number of genes with a z-score of below -2. Oh, the other. Let's see what. Just for okay, there's no genes that are too large. Okay, this is, yeah, so with large we don't get Yeah, okay, you can see that, this is not a real normal distribution. Alright, let's clean up here. Okay, here this is, let's clean up here. Okay. Polars. All right. Okay. This is um, I just okay. Yeah, this is okay. Okay. Okay, this is what I wanted. Okay, let's just gonna exit, and just to be sure, I'm gonna run everything from scratch, and then unless this errors out, okay. Okay. In the meanwhile, this also ran one. Okay, so yeah, so you can see there's 48 to run. It ran one. As I said, the chunks don't take the same size, so this chunk 00 was shorter, but still nice to see that it actually did run. Let's see. Okay. Also, the outputs are here. Okay, so everything's good there. We will run that. In the meanwhile, okay, evaluate. All right. Okay, and this might actually be, right, so this might actually be the solution. So we find KOs with very stable gene sizes by looking at the GMGC as a database, and then we use that and we look at Z-scores instead of percentiles. And then if we have KOs that are very stable, then that might be the solution. Right? Okay, all right, so this is running. Okay, so you can see E. coli. Okay, for minus. So what we want to see is something like -3. The wild type is always in this, always in the single digits. Stereo, yeah. See. Yeah, this is. Right, so, right, maybe. So there's something here. Right? This is no longer. This is no longer so dependent on the. Yeah, stuff. Yeah, so it's always the same. Much more. Yeah, so looking at the Z-score is much more stable than the percentiles. So maybe. Okay. So this is very promising. Yep. Scores to quantify gene size per kilo. Okay. Actually, let's see. Appears. Okay, yeah, did I not post a recap for this one? Okay, maybe I just never. Okay, I'll upload that as well. All right, so that's it. Push up. Yeah, I'm gonna do this here. Okay. All right, and so with that, so reminder, everything is on GitHub. So we have the channel. Please subscribe. I'll be posting other things. I also post other things in the channel other than the streams. I'll post a recap video later in the week. Hopefully also with an update on how this is running. Oops. How this is running. How the GMGC is running. I post on the Discord. And again, if you have any questions about any of the other stuff we do in the lab, be it you're using SemiBin and you're now I see that the camera has always been a little bit. But you use SemiBin and you're running some problems, or you're using GMGC and you want to know if you can do X, Y, Z. Please get in touch, email us, right? And yeah, with that, so I hope to hear from you soon. Talk next week.